to smectic to crystal. This next one is stolen from the Royal Society of Chemistry, and it just shows disks or smarty things going into columns rather schematically for a kind of typical disk-like thing. And what I want to do here is just look at some other shapes, in particular looking at shapes that may or may not give the biaxial nematic phase. And this is going to be a quick scamper, even quicker now given my kind of rather faulty start, through V shapes and some kind of fused hexagon systems, which I'll try to explain why we did it, but I can't really. There's no rational reason for why we chose those shapes. So I want to begin with V shapes and the biaxial nematic phase. And as we've heard before from Dr. Belli and Professor Van Ackerath, you need a biaxial shape and a V-shaped molecule, something like that, fits the bill. It's a biaxial, and so in principle can form a biaxial nematic phase where all three axes of the molecules are aligned on average, but you have center of mass liquid-like disorder. And as has been mentioned before, this was first mooted by Frisia back in 1970. And the experimental setup, again, to recap, these are these lovely experimental systems studied by van den Poel et al., and they observed biaxial nematic phase in goethite, which is roughly a board-like molecule, board-like particle, rather, sorry. And those were discussed very ably by our two previous speakers. Experimentally, this has caused great controversy. I'm not up to play with this. This particular bent core molecule has indeed been claimed to form a biaxial nematic phase. I know there's a lot of doubt about it. I don't know what the current thought about the system is. Maybe Mark or someone else in the audience will know. It's certainly not sure. The experimentalists, I think, are still out on whether that thing really does form a biaxial nematic, though I'm not completely up to date. So this was an idealized phase diagram. This is some work that Paolo Teixeira, also in the audience, and Bela Mulder and I did back in the deep mists of time, when we just considered a spherocylinder dimer and tried to work out using Onsager theory, that's just a second virial theory, what would happen to the phase diagram as you changed the bond angle. And this is a kind of generic diagram. I can't remember now, maybe Paolo can, with all the dashed lines and the dots and things on it, but the basic point is that you get a magic angle, which corresponds to about 110 degrees for this system. You should be able to get a direct transition from the isotropic to the biaxial phase. If you're off, then if you're lucky, you might be able to compress the system and go through a nematic phase and then hit the biaxial later on. As I say, this was done by us using Onsager theory, second virial. Paolo did the clever analytical stuff. I just crunched the thing out numerically. But, qualitatively, you got the same kind of stuff. Jeffrey Luckhurst had a completely different approach, a molecular field approach. We ended up with something very similar, miraculously. Again, the magic angle being about 110 degrees. Now, I would claim, well, there it is, the biaxial phase schematically. I would claim that our treatment is exact in the limit of long arms. We're dealing with repulsive hard spherocylinder arms. And I think the same argument goes through that Dan Frenkel said in his talk, that for sufficiently elongated arms, the transition takes place at low packing fractions, so there are no smectic phases or anything around. And that what we've got is an exact result. That's been tested by going to third virial level. I haven't done all the way like Dan did by going up to fifth or anything like that for these particularly odd shapes. But I think, though this might be debatable, that that's an exact result in the Onsager limit. So I think the biaxial phase is there. But the question is, how long in practice do the arms have to be? Can you see such a phase in a computer simulation, for example? I also would hope that you could see it eventually in experiment, but then I think you'd need to build these V-shaped colloid particles. I don't think we've got them at the moment, or at least not long monodisperse ones. So we had a go at doing simulation studies on bent core models, and this has been done before. Mike Allen and I and Philip Camp had a go at that many years ago. I'd also mentioned the work by Lansach and Camp and Dewar. And while writing this, I also realized I was being neglectful because I had in my mind just hardcore models. That I should also have mentioned the work by Memmer on gay-Byrne potentials, and of course the recent work by Professor Longer, also on gay-Byrne dimers. And I kind of neglected that, and I should have referenced it, and apologies. No doubt there are other people I should have referenced here as well, so I apologize for that too. And we're going to do what I want to look at is a bit of the dependence on the bond angle and the arm length. We go on then to what happens if you've got binary mixtures of these V shapes. And my house rules are that we're going to obtain all phases by compressing the isotropic. We're not allowed to begin by melting a crystal. So that's just what we imposed on ourselves. We wanted to make sure these phases were forming spontaneously and weren't a result of having chosen a particular starting configuration. That's what we were trying to do. And that was our particular model. We composed our V-shaped molecule just out of repulsive beads. The beads interacting by a Weeks-Chandler-Anderson model, a repulsive potential. 180 degrees is flat, is a straight line. 90 degrees is at right angles. Okay, and so we just let rip. The nice thing about using these potentials is that you can use molecular dynamics. Many of the other simulations were done with Monte Carlo, and it was our hope that maybe molecular dynamics could allow for equilibration that little bit easier. At least that was our prayer. As I say, we're not very good at simulation. At least I'm not an expert. I don't know how to do free energy calculations or anything like that, nothing clever. All we're doing is simply using standard techniques, compressing the system because it's basically an athermal repulsive system, and just seeing what we get. All I can say is we do try our very, very best to do the kind of normal things that an amateur can do. We do try, for example, to check system size. When it comes to ordered phases, we will look, for example, at constant strain simulations to allow the box to change shape. And we do try to check number size, and we do try to check hysteresis. So we do that kind of standard stuff, but as I say, nothing intelligent. So, just to kick off, these are our simulations to begin with. These are 140, so by no means straight, but not anywhere near the magic angle of 110. And what happens then is you compress, then you get to the nice pneumatic phase. It's color-coded, so that if the molecules are aligned, they are blue. If they're perpendicular to the director, they're red. So there's a good lot of blue there, and it's a pneumatic, uniaxial pneumatic. If you crunch it further, it doesn't go biaxial, it forms a smectic. Rather dislocated, that's just because we were a bit careless in that shot. If you do it more carefully, you get a proper smectic. So nothing doing there, for biaxial at least. If you try to go down to the angles you're interested in, you just get a tangled mess, which is actually the problem we've had in previous simulations. So this was 130 degrees, and you get these little clusters as you compress, even more so at 110. It's just not equilibrated. It's just jammed. So this is where I need help, because I'm stuck. We took this problem actually to Jeff Errington in Buffalo, and one of his students had a go of it, and he was trying to do all kinds of clever ensemble hoppings and all the kind of neat stuff that they do over there. As far as I know, they haven't succeeded either. So if anyone could either tell us what we have to do to equilibrate these more bent systems, or else preferably, given our level of ability, do it for us, we'd be extremely grateful, because that's for us the kind of crucial angle, 110 or so. That's when you really expect to see something interesting. And we just can't get there. So that's my first admission of failure. Many to come. That's a better looking smectic for a longer system and more careful preparation. So what I wanted my student to do was to run these simulations for longer arms, and he told me he couldn't do it because he wouldn't fit or take too long or something. So we did shorter ones instead, which is, I suppose, rather easier. And you get the same kind of stuff as we had before, n equals 7. Again, you compress to get smectic phases when the things are roughly straight. When you get anywhere near an interesting angle, you just get a jammed muddle. Again, we want to cure that, but we don't know how to. So we gave up at that point and wondered about what happened if you started mixing these V shapes together. And this comes back to the talk of Dr. Belli. And the idea is that if you have a mixture of particles which are different shapes or different lengths, then they may not sit very easily in a smectic layer. And so maybe that will extend the region of stability of the biaxial nematic, allow you to find it. So maybe you could compress your uniaxial nematic of a mixture, and rather than going into a smectic, it would go into a biaxial nematic. At least that was the hope. In what follows, we just considered 50-50 mixtures of particles. Of course, we could vary the mole fraction, but we thought if anything was going to happen, it's going to happen at 50-50. And so we just plugged away. We began with the long molecules, n equals 11, and had a mixture of 11 and 7. When you compress, to begin with, they go from isotropic to uniaxial nematic, as you might have expected. You compress a bit further. No biaxial nematic, the thing phase separates. You get coexisting smectic phases. Blue is the long molecules, red is the short molecules. It's not like a proper simulator. I haven't tried to do it properly, but it's obvious, I think, that this is phase separated into two coexisting smectics. So that's no good. I suppose it's vaguely interesting, but it wasn't what we wanted. Tried it again with shorter molecules, n equals 5, n equals 11. The n equals 5 system, if you compress it, doesn't form a nematic phase at all. If you mix it with these long n equals 11 and you compress, then you get a nice mixed smectic. The long molecules kind of absorb the little ones and make them nematic as well. If you press even further, though, the big blue molecules kind of fall out as a smectic, leaving an isotropic solution of the little ones behind. So that didn't work either. So there we are. So the summary is, when you increase the pressure, a smectic precipitates out, and we never see a biaxial nematic. And you get similar things if you vary the shape in another way. You might try changing the bond angles rather than the arm length. You get the same thing. It just phase separates, and you don't get the biaxial phase, at least not for the parameters we've tried. Now, I could ask about the effects of higher levels of polydispersity. Suppose you mix more of these things together, and Christine Stokes, who is my long-suffering PhD student, will give a presentation on that on Friday afternoon. We had a look at other models, but they didn't give any biaxial phase nematic that we could find either. So moving on to boards and hexagons, which is the second bit, which is again somewhat similar, but actually slightly different from the lovely talk by Professor Van Ackeras. Again, we wanted to do something that resembled a board. And to recap, if you have a real board, there's a dual point where if the ratio of C to B is the same as A to B to A, then it's a kind of slightly schizophrenic kind of shape, and it's theoretically predicted that this will conform a biaxial nematic phase in which all the faces line up, but there's still positional disorder, and indeed that was found experimentally and indeed by simulation, as Professor Van Ackeras showed. We, for reasons that I can't rationally explain, decided to look at these hexagonal systems. And like Hanover at BM, it's not for kind of any scientific reasons, it's for more the way the PhD was going reasons. This was done by my PhD student. And we just ended up looking at these fused hexagons, and you can vary the shape from something which is disc-like, which is just a single hexagon, to something which is increasingly rod-like. And those are the systems we studied. And the details of the model were these were rigid shapes. Again, our spheres interacted by the Weeks-Chandler-Anderson repulsive potentials. We could use molecular dynamics. And we again did the same kind of moronic stuff we did before, NPT simulations, but checking for hysteresis, number size dependence, constant stress every now and again to check the box shape wasn't affecting anything. And that was the pair potential between the beads. And these were our structures again. This is, if you compare to a board, is definitely rod-like. That is like a disk. That is very near that kind of dual point. And this is on the rod-like side, roughly speaking, if you map these dimensions roughly onto a board. So we just went ahead and did it. So we began with the disks. The little disks are too small to do anything in terms of liquid crystal phases. So we built a bigger disk by putting another ring of disks round. And that went from, no pneumatic was formed, it just went directly to a columnar phase. Not the greatest picture that I got him to do it again, and I think it's a bit better equilibrated pictures we've got now. This was left over from before, but it's still columnar. Let's move on. So I want to move on now to the rod-like system. Oh, goodness me, that's gone ahead of, come back more slowly. So that should be roughly rod-like. Something of that length, that collection of hexagons. And you compress it, and it does the standard rod-like stuff. It forms a uniaxial rod-like pneumatic. The color coding is you can color code according to what director, what axis of the molecule you think is lining up. So this corresponds to color coding is blue if the long axis is lining up. This is if one of the shorter axis is lining up. That one's definitely lined up. This one is essentially, we always run into this. It's a very low biaxial order parameter. We don't think it, we think it's essentially zero. We think it's uniaxial. If you crank it up, you get a smectic A, again, the uniaxial smectic A. If you crank it up a bit further, it starts to tilt. So you begin to see smectic Cs, and again, we check this by doing constant stress simulations. This is kind of typical of having these corrugated surfaces. When you have rods and things made out of spheres, they have a tendency to tilt in order to pack better. These boards are just the same. So I don't think you wouldn't get this, I think, with flat faces. This is a result of the corrugation. And finally, the thing crystallizes. So it's all the kind of standard rod-like stuff, possibly with the exception of smectic C. We then went on to the 2 hexagon, which is a bit like a disk, if you just believe these sort of rough mapping onto boards. And to begin with, it's isotropic with all these multicolors. If you increase the density, then it forms what is essentially a discotic uniaxial pneumatic, again, as you might expect. Again, patches are green, but the biaxial order parameter is really pretty low. Certainly less than 0.1, so we think it's uniaxial. If you carry on pressing it, though, you get this. This doesn't form the columnar phase, which is what I'd have expected, which is typical of disks. You get these layered smectics. So these disks are lying flat in mono layers. So it's a kind of discotic smectic, if you like, or a lamellar phase in a sense. Discotic lamellar phase, which I thought was certainly unexpected for me. No columns. So that's what we got for that system. We then went on to the 3-disk system, which is the closest we've got to the dual point for a board. Again, you compress, and it is either, again, a discotic pneumatic. The biaxial order parameter is about 0.1 again. it's greeny, that left-hand cube, so you could argue possibly it's biaxial. We think not. It's hard to know with these rather low biaxial autoparameters whether they're for real or not. At least we find it so. We think this is a dystotic nematic at first, but there is a little bit of doubt because it is a bit greeny. If you crank it up, though, you get a smectic, again a layered smectic, but there are this time, there is definite biaxiality this time in the layers. So you're getting a biaxial but layered smectic. So order parameters round about 0.25 or so. So again, I think from our point of view, that was big enough that we have to take it seriously. Do we think it's a biaxial but layered smectic forms? But we didn't get a biaxial nematic, at least not convincingly so. So finally, the 4-disk system, which is big enough, we think, to map onto something which should be rod-like. It forms, at the beginning, what looks to us like a uniaxial rod-like nematic. Quite blue. Not much happening to the perpendicular axes. If you carry on compressing it, then you do get a definite biaxial nematic. Everything's very blue for all directors. So we're very confident that that is a biaxial nematic this time, which is got into by compressing what looked like a uniaxial nematic. And then at the end of the day, we get a biaxial smectic phase. Not the most brilliant picture, but our analysis was that this was a biaxial smectic A. And those are just some order parameters to show that we actually have been doing some work besides just taking pictures. I thought it would be boring to show that all the time, but we did it. So here we're getting that kind of sequence of phase transitions, so far as we can tell. So there we are. It's getting all kinds of stuff. And if you go back in the literature, and again, this was mentioned in the previous talk, there's this absolutely remarkable paper, I think, by Taylor and Hertzfeld in the 1991. They used mainly a free volume technique to calculate the stability of all conceivable ordered phases. They had some kind of scale particle theory for doing the isotropic nematic stuff. And they predicted this very, very full phase diagram for spheroplatelets, which are kind of boards with rounded edges, very close, I think, to what Professor Vanakeros was talking about. And it looks a bit odd down here because they're trying to match up one kind of theory with a different kind of theory. So that part of the diagram, you know, is a bit weird. But what is interesting, I think, is that they say that if you compress this stuff, then you end up with a kind of smectic layer, at least on the phase diagram. It contains a standard smectic. It has biaxial smectic. It's also got this dystotic smectic that we found as well. I don't think Professor Vanakeros ever saw that one, so it's kind of interesting. So they predicted. Oh, right done. Almost at the end. Anyway, they predicted this layered smectic, not the kind of columnar phase that anyone who's used to disks would have expected. According to their phase diagram, you only started getting columns if you compress still further. And then eventually it became the crystal. So I thought that was a real tour de force on the part of Taylor and Hertzfeld, actually. I was very impressed with that paper. If I want to compare with our results, then, of course, it's not quite the same system. We only saw a columnar phase for large hexagonal disks. We never saw any smectics wanting to turn into a columnar on further compression. So we didn't get that. But everything else they had, we saw at one point or another. So the summary. For the bent core models, I believe, I'll stick my neck out, that theoretically the biaxial nematic phase exists for hard body dimers in the Onsager limit. We can't see it because we're hopeless and we're not able to simulate the 110 degrees properly, and I hope that someone who knows what they're doing can do it for us. We can't do the proper bend angles we want to. If we try to extend the biaxial nematic by using a binary mixture, the system kind of gets its own back on us and simply demixes to form a smectic. For the hexagonals like the board, you get a whole interesting collection of phases, very little columnar apart from our single hexagons. And we do get this layered smectic phase, predicted by Hertzfeld and Taylor, but at least to me, rather unexpected. It seemed to form that rather than the columns that I would have guessed. And finally, the acknowledgements. A lot of help from Mark Wilson, who kind of is our guru for getting started on molecular simulations. And the two PhD students, Robert Sargent and Adam Rigney, who did all the work. So thank you very much.
Thank you for your talk. We still have time for questions. So
is your four-disk system self-dual, more or less?
No, it's rod-like if you just believe the mapping onto the board. Of course, it's not a board, but it doesn't seem to go directly into biaxial nematic.
What is the sort of thickness compared to the width?
I can't remember that offhand. It's I can tell you that later, I'm afraid. It is on the rod-like side, but then, of course, it's only an approximate mapping, given the fact it's not a board.
Yeah, I've got two questions, if I may, both related to the bent rod system. First one, of course, you started out by saying you believe in the Onsager limit that the results are correct, but then that leads to the question, how can you get to the Onsager limit? And remember that when Ronald Black and Bella Mulder and company were looking for the cubatic phase with Onsager crosses, they did a calculation of the virial coefficients of that system and found that in order to neglect third and higher coefficients in the expansion, the L to D ratio needed to be about 1,000. So that is way longer than what you're simulating. And I wondered if you'd done the same calculation for your bent rods. Second question, if I can just get it in quickly, on the right-hand side of the phase diagram, of course, leaving aside the difficulties of getting the biaxial nematic phase, you also had a discotic phase.
Yes.
And I'm just wondering if you've ever managed to see that using a system of two rods.
No, very good questions, as ever, Mike. The first question answer, no, I've never done that detailed calculation. When you and I did it, actually, in one of our papers, we did look at the effect of the third virial coefficient. And as far as I can tell, when you extend it out to infinity, that plays a negligible role. We didn't try, because I just wasn't thinking that way, because I wasn't thinking about simulations at that time at all. I never bothered to work out how long it had to be to make that negligible. Still, with the third virial, you just still thought there was a good chance of seeing the biaxial nematic. But yeah, I take your point. For the discotic phase, I must confess we never tried. This would be the idea of having a rather small bond angle. No, we never looked at that.
I have two questions also, if I may. One is for the virial expansion. Does that phase diagram include the possibility of crystalline phases? I didn't notice that in what you presented, right? And so if it doesn't, then I'm not exactly sure of what the relevance is to the experimental question of whether a biaxial nematic phase would exist or not, right? Because there's no question but that a low temperature phase has biaxial order, right? The question is whether it's a biaxial nematic or a biaxial crystal, right? And that's the hard thing to do is to keep the biaxial order while spoiling the crystalline order, right? And so your simulations address that, but I guess the virial expansion does not.
The virial expansion has terrible difficulty technically in dealing with a positionally ordered phase. I mean, you might be able to, possibly, but it's certainly technically very difficult. No, the calculations I presented are very much for disordered phases, and they're only strictly valid in that Onsager limit of very, very long arms where the transitions happen at very, very low volume fractions. it is, as I think as Professor Frenkel said, that is a limit that we are looking at there. If you want to extend that kind of theory to more realistic systems, I mean, that is incredibly hard, I think.
And then a second question. Have you tried looking for the flexoelectric effect in these simulations? Because I think that's, for the bent core particles,
Yes.
I mean, I think that's something else which is getting experimental controversy, and so yet another controversy that you could weigh in on.
Yeah.
And you know, but regardless of controversy, it's another area where bent core particles could be expected to show remarkable results, and I think could be quite amenable to this sort of simulations that you're doing here.
It's a very nice suggestion. Mike, didn't we do something like this at one point?
Yes, we did, too, but I think our problem in those days was simply getting a wide enough pneumatic range for the bent core molecules before they got entangled. So I think we intended to calculate those things, but we never got right to the end of that project.
I think it's one of those things where we applied for funding and never got it, and therefore kind of despaired, wasn't it? It's a very good suggestion. Maybe we should take it up again.
Did you try to estimate the biaxial order parameters?
Yes, we did do that.
And what are the values?
Well, they came up to about 0.4, 0.5 or so when it was clearly biaxial. But there are all these murky areas when they're about 0.1 or 0.2, when I suppose it's a difficult, or at least we found it a difficult call to know whether that was significant or not. And maybe you could advise me on this. I find it very hard if you've got something about 0.1 or so to know whether that's real or not.
Another question, if I may. Did you observe any causality, spontaneous?
Once we did. We got very excited about that. There was a spontaneous twist. We only ever observed it in one single simulation. We could never reproduce it, so I didn't mention it. But we thought this is wonderful, but then it didn't happen again.
Yeah, it's so the comment is about the comparison with the real bent core, as it were.
Yes.
That is a thermotropic.
Yes.
Your simulation, you don't have temperature, right? You change you essentially change the pressure.
If it maps onto anything, it will be some colloidal system.
Exactly. But then when you have the other, the disks, the hexagons patched together, the thermotropic analog of that would be what are called acids, so benzene, naphthalene, anthracene, tetracene, etc. And none of this gives a liquid crystal phase. They give crystals, of course, which could be biaxial. Typically, I think they have actually an herringbone, but they could. So maybe the fact that you don't get what you want is kind of reasonable in a sense.
I understand what you mean. I think, of course, there's a terrific amount of dispersion in those systems you just mentioned, trying to put faces
These
against.
are chemical molecules. There are no dispersion. They are exact.
I mean there are dispersion forces between the aromatic rings.
I thought you meant polydispersity because of...
No, sorry, I'm being a chemist, I'm afraid. And that is, of course, a very important effect that we're completely neglecting. Now, historically, Adam, when he started off, one of the reasons he looked at hexagons was for this kind of reason, and he had Leonard-Jones potentials, and I must confess, our simulations got even more stuck than they normally do, and we thought, oh God, this is going nowhere, so we went off to something that we thought would work. But right, what you say is very, very valid. If you wanted to make contact with real molecules, then we need proper intermolecular forces.
You showed that rather interesting kind of smectic that didn't quite form a smectic when you compressed it for the bent core systems.
Yes.
It was sort of interesting because there was this theory by Professor Elgaris and Dimitri Fotinos that predicted you could get this intriguing thing where you went from a uniaxial pneumatic to another uniaxial pneumatic, but it could be a system in which you had biaxial clusters. So it was a phase stabilized, which was uniaxial in nature, but it was kind of made out of these clusters.
Yes.
And it looked almost as if you could be very close to having that phase within the simulations. So I'm wondering if there or thereabouts you could have something that's still fluid, but is made out of these clusters, which are themselves biaxial, and in a real system could potentially be ferroelectric.
I mean, it's possible, Mark. I don't know is the answer. I mean, it's very hard to tell. I mean, in our systems, we always thought that if we equilibrated properly, all this disappeared, and we found a conventional
Is this
phase.
still fluid at that point? Can you measure the diffusion coefficients?
I'm sure we did, and I can't remember what we got. I'm sorry.
Okay, and one more question, just related to those phase diagrams. In the system that did go biaxial, you had something that went from a uniaxial to a biaxial phase. But on that original bent core system, it always intrigued me that phase diagram seems to go directly from the isotropic to the biaxial phase. And that seemed also to be Lucas' predictions as well.
At the magic angle.
At the magic angle.
Or at the magic self-dual point for a board.
I mean, is that expected? Is that...
Well, I think I'm going to have to pass over to more experts on the... I mean, Professor Berger, I think, has worked a lot on this. I mean, you can get scenarios where you get a line of first-order isotropic biaxial transitions, I believe. And so there are various scenarios. This just happened to be the one that we found for that particular shape. But it doesn't have to look like that. But Professor Berger is the expert, I think, on, well, certainly is one of the experts on that kind of thing. Pass over to him on that.
Any more questions? If not, then that's time for coffee.